I am from Department of Pure and Applied Physics, Guru Ghasidas Vishwavidyalaya, Vilaspur, Chhattisgarh, India. And it is located in the central part of India. First, I would like to thank to the organizing committee of this international conference on material science and engineering for inviting me as a invited speaker in this conference. The topic of my presentation is modification on the electronic property of CVD grown single layer graphene by deposition of thin transparent conducting polymer. The outline of my presentation is the introduction to the graphene and application of the graphene as a transparent electrode. Then I will discuss about the modulation of graphene electrical property by some conducting polymers. Then I would like to conclude my presentation. So next slide is the introduction to the graphene. It is well-known material nowadays. Graphene is a single sheet of a carbon atom, and it is a basic building block of all other form of the carbon nanostructure like zero-dimensional C60. When we wrap the graphene sheet, we can make the zero-dimensional material, zero-dimensional nanostructure. If you roll the graphene, we can make the single wall carbon nanotube, maybe the one-dimensional nanomaterial, and we stack together so we can make the graphite or a bulk material. And it is a thinnest material. The thickness is around 0.34 nanometer for the single layer graphene, and thickness increases with increasing the number of layers. Then the electrical property of graphene. Graphene is classified as a zero band gap semiconductor material, and is a unique band structure. The electrical conductivity is very high at a room temperature, around 25,000 centimeters square volt per second, a room temperature, and at a low temperature it may be around 2 lakhs centimeters square volt per second. And in case of suspended graphene, the mobility is even much higher than the reported value. So it is very conducting material. And the mechanical property is very flexible. The Young modulus is around 1000 gigapascal. And graphene is the strongest material ever measured and is 200 times stronger than the structure steel. The optical property, it is highly transparent. The transparency of single layer graphene is 97.97%, and transparency decreases with increasing the number of layers. When suppose it is a 2 layer, then we just multiply 2.3% with the number of layers, so transparency will decrease with increasing the number of layers. So it is highly transparent. Single layer graphene is highly transparent. So people are working in the application of graphene in a many field, and it covers almost all area of science and technology, like gas sensor, gas detection, graphene transistor. Although graphene transistor not much successful because of zero band gap material, and on-off ratio is very low in compared to other semiconducting material because of low zero band gap in a graphene. Integrated circuit can be fabricated by using the graphene, and the most important application of graphene is a transparent conducting electrode and ultra capacitor graphene bio devices, and even it can be also used for the nano composite devices, nano composite material, and for many other applications. So I will focus only on the graphene as a transparent electrode material. The graphene as a transparent electrode material can be used either in the solar cell, light emitting diode, or electrochromic devices, such as screen and supercapacitor. So why we require the graphene as a transparent electrode? Because of high conductivity and flexibility, and good optical transparency. So these are the requirements for any conducting transparent electrode, and all the property have this single layer graphene. So graphene has a transparent electrode. Already many researchers are working in the area of the graphene as a transparent electrode. Graphene can be synthesized at a very large scale of large size, the CVD method, and it can be transferred on any substrate, either on the plastic or on the silicon substrate or any substrate. We can easily transfer from another one substrate to the another substrate. And we can fabricate any type of the device by using the graphene. So why we require to tune the property of graphene? Because to increase the performance or to improve the performance of any electronic devices like field effect transistor, solar cell, light emitting diode, we have to optimize the charge transport from active material to the electrode material. So we can tune the Fermi level of the graphene, so we can tune the performance of the device. So the doping is important in a graphene, because graphene, if you want to use graphene as an electrode, so we can tune the Fermi level of the graphene, then it can be modulate the performance of the device. When we require high Fermi level or low Fermi level, accordingly we can tune the Fermi level of the graphene just by the doping. So people have already worked a lot in the area of doping in a graphene. I have given some example here. We can see the doping of graphene with the potassium. So this is the pristine graphene. The slope of this curve actually decides the mobility of the charge carrier. So when we dope the Dirac point, this is the Dirac point shifted toward the negative gate voltage. When further increase the doping, it again further move to the R negative voltage. But here one interesting thing, the mobility decreases because the slope is decreases. So we can tune the property, but we reduce the mobility. Another group have also did some work when we annealed the graphene in the atmosphere, in ammonia atmosphere. So here we can see the Dirac point shifted from positive to negative because of the N doping, electron doping, but the electronic structure will change. Here some nitrogen are replace the carbon atom. So that maybe reduce the mobility also. And another group have also used the light sensitive material. The light sensitive material just deposited on the graphene, and then when we switch the light 360 nanometer or above the surface, then this molecule shifted from cis to trans conformation, and that tune the actually the Dirac point. So here interesting thing is the mobility is not much influence by just changing the light or changing the conformation of the molecules. And another group use the argon plasma with the malinium molecule to dope the graphene, but here the mobility is much reduced. And then some group has used the aluminum gold chloride and then tuned the property of graphene. So in this direction, we have also did some work, and we have choose the P.PSS is a well-known conducting polymer, and it is highly transparent. So we just want to use both materials should be transparent. The graphene is already transparent material, and P.PSS is also a transparent material, so that we don't want to change the transparency. That's why we use the P.PSS, and P.PSS is also have a good conductivity around 1000 Siemens per centimeter, and it is easily deposited on any substrate just by the spin coating technique or by drop casting technique. So it is very suitable material to dope the graphene. And people have already worked a lot with the P.PSS in graphene, with graphene oxide and graphene quantum dot, and used for many applications in almost all area of the science and technology in area of the optoelectronics, in the sensor, in the flexible electronics, electrochemic and electrostatic devices. So, but they have not discussed actually what the property change when we deposited the P.PSS over the graphene surface. They have only fabricated the device and measure the performance of the device. But what at the molecular level why the property are changed, they have not discussed. Only the few literature just discuss the why the property are changed when we doped with the P.PSS. So our focus is when we doped with the P.PSS or when we spin coated the P.PSS over the graphene surface. So how much property changes when P.PSS coated over the graphene surface? So why P.PSS? We have already discussed, because of the transparent material, and we can tune the Fermi level of the graphene, and we can increase the solubility of the graphene also. And the surface modification is a very simple and effective technique to tune the electrical property of graphene. That's why we choose the P.PSS. So after we have chosen two concentration, 0.7 weight to volume percent P.PSS and 1.0 weight to volume P.PSS concentration. So this is the Raman spectra of the pristine graphene. This is the 2D peak and G peak. The difference between 2D and G peak, there is intensity difference, indicate the single layer graphene. And when we doped with 0.7 weight volume percent and 1.0 weight to volume percent, the 2D and G peak shifted toward the higher wave number, which indicate the P doping, means the whole doping in the graphene. And then we have also calculated the ID by IG ratio, and both indicate the doping of P.PSS over the graphene surface. So here we can see the 2D peak is not much shifted in compared to G peak. So G peak shifted around 4 centimeter inwards, and in case of 0.7 weight to volume percent, and in case of 1.04 weight to volume percent, it is shifted around 5 centimeter inwards. But the 2D peak shifted around 1 centimeter in case of 0.78%, and 2D peak is shifted around 2 centimeter inwards. The many literature have reported the shifting of 2D and G peaks not indicate the doping. When there is a large shifting in a G peak in compared to 2D peak, then only indicate the doping of the graphene. So in our case, it is perfectly matched with the literature and with the other literature, and it confirmed the doping of P.PSS over the graphene surface. The 2D peak shifted may be due to the strain induced in the graphene surface, but when both G and 2D peaks shifted, it means there is a doping of P.PSS. And we further confirm by the morphological characterization. Here we can see this is the pristine graphene. Then we spin coating of the P.PSS over the graphene surface. This is the small particle indicate the P.PSS molecule. Then this is another concentration of P.PSS, and this is the SCM image. This indicates the P.PSS over the graphene surface. And the image confirms the homogeneous distribution of P.PSS over the graphene surface. Then further, we confirm the doping by electrical transport measurement. We have measured the backgate versus drain current. This curve represents the pristine single layer graphene. The Dirac point is near about around 5 volt. When we doped with the 0.78%, it shifted to the 25 volts, the plus 25 volts, and after 1.08% doping, it's shifted toward the around 30 to 30 volt, plus 30 volt. So Dirac point shifted toward the positive gate voltage indicate the whole doping in a single layer graphene. And we have also calculated the carrier concentration with as a function of P dot PSS concentration. So the carrier concentration increases with increasing the doping concentration of P dot PSS. And we have also measured the mobility by using this formula 1 upon Cg delta sigma upon delta Vg. The mobility will increase with increasing the P dot PSS. It means our P dot PSS doped graphene can be used for the transparent electrode. And we have also confirmed the Fermi level shifting just by measuring the Kelvin probe force microscopy. We have measured the CPD by Cg into CTP. So we measure the work function of pristine graphene is around found to be 4.86 electron volt. And when we dope with the P dot PSS, its value is 5.06 electron volt, and then it further moved to the 5.08 electron volt. The Fermi level shifting from 4.86 to the 5.08%, which indicate the doping of P dot PSS molecule over the graphene surface. And its value, the highest value of work function 5.08% is very much near to the work function of gold. Gold is mostly used for the electrodes in the many electronic devices. So our electrode can be also used for the electrode in many electronic devices like a solar cell, light emitting diode, field effect transistor, and many other electronic devices. The conclusion of my presentation is the modulation, the electronic property of graphene is essential in order to obtain the best performance with electronic and optoelectronic devices, as well as enabling the fabrication of various complex devices. We have investigated the effect of different concentration of P dot PSS, mainly 0.78 weight to volume percent and 1.08 weight to volume percent doping of the, and we change the electronic property of CVD growth single layer graphene. The electrical transport and Raman spectroscopy measurement revealed that the P dot PSS coating imposed the P doping on the CVD grown graphene because the 2D and G peak shifted toward the higher wave number. And in electrical transport measurement, the Dirac point shifted toward the positive gate voltage indicate the P doping of P dot PSS. We have observed that the P dot PSS doping significantly modulates the work function of the graphene. Our study will provide the better understanding to it, utilizing the CVD grown graphene coated with P dot PSS as a transparent electrode in a future flexible electronic and optoelectronic devices and many other applications. I would like to acknowledge the Professor Janwa Om, which provides the CVD grown graphene from the Graphene Research Institute, Sinang University, South Korea, and Professor Rajiv Prakash, IIT BHU, provides some catalysis facility. And I would like to thank to the our funding agency, CRB, SARG project, and UGC DA CSR project. And also I would like to acknowledge our collaborator. And without these students, this work not will be possible. So I would like to acknowledge our student also, the PhD student, Mr. Dr. Vivek Chowdhury, is a scientist in Morocco in ultra-fast spectroscopy. Dr. Anand is the assistant professor in university. These three students are currently working with me. And thank you very much. If you have any question, you can ask.